Cool. I think let's get started. Morning, everybody. Yeah, I just firstly for everyone to know, this seminar will be recorded and added to the SAEON YouTube page. And so hope everybody's happy with that, and other people can check it out afterwards. So my name is Julia Glende. I'm a research associate with the Fynbos node, and it's my pleasure to introduce Faith, who will be speaking today. So Faith Jumbi is a postdoc who started with SAEON in 1st of May, and she finished her PhD also linked to SAEON at UWC, graduating beginning of this year. So she'll give the presentation, and then we'll have some questions and discussions afterwards. And if you have questions during the presentation, please put them in the chat, and I'll hold them till the end of the presentation, unless there's something that really needs quick clarification. Then Faith, I might interrupt you for that if one comes up, but otherwise questions at the end. Thanks, everyone. Faith, I'm handing over to you. Unfortunately, her camera's not working, but hopefully you'll get to meet her in person sometime soon. Thanks.
Thank you, Julia, for the introduction. Hello, everyone, and thank you for joining us today. I'm going to start with the presentation. So land use and land cover types, they influence a variety of landscape processes, and the combined effects of these land uses and land cover types, they determine the net impact on water resources. Generally, the effects of land use and land cover types are known, but the prediction of this in a specific catchment is problematic. So numerical models have been used, and they aim to represent the many interacting processes, and can be used to predict impacts of land use and land cover changes on processes. However, there are high levels of uncertainty due to model structure problems and lack of long-term data. So to reduce uncertainty, long-term hydrological data is required to run and calibrate these models better. However, few cases in which changes across multiple contributing processes have been measured here in South Africa, particularly in mountainous catchments, which provide significant challenges for modeling. But SAEON manages some long-term research catchments, such as the Cathedral Peak in the Drakensberg Mountains in KZN, and the Jonkershoek in the Cape Ford Mountains here in the Western Cape. And these provide a unique opportunity to study the impacts of land cover changes on hydrological processes. So the proposal for the current study was developed after the completion of a project for my PhD, where I was characterizing flow paths to improve the prediction of vegetation impacts on hydrological processes in mountainous catchments. So I'm going to give a brief summary of the results from this study, as we are going to use the same approach for the Cathedral Peak and the Jonkershoek catchments. The Crom catchment lies in the Eastern Cape province of South Africa, and it's regionally important for water supply, as the two dams, the Churchill and the Impofu Dam, they supply water to the Nelson Mandela Metropolitan. So we set up some monitoring equipment, and we collected various types of field data. And I'm going to present just a few of the results. So we collected isotopic data. So we have isotope signatures along the river profile and from the tributaries, boreholes, and piezometers. We also collected hydrochemistry from different sources, such as surface water, shallow groundwater, and deep groundwater. We also monitored soil water content under different land cover types, as well as water elevations to determine the hydrological connectivity between the river and the alluvial aquifer. So using all this field data, we developed a conceptual model of the catchment to show the dominant flow paths and the relationship between the river and the alluvial aquifer and the bedrock aquifer. So using the field data collected and literature and our developed conceptual model, we set up the model structure for prediction in MikeShe. And then we came up with 3 scenarios of land cover change. The first one was a regeneration of palmite in the floodplain after clearing of alien trees. And then the second one was invasion of or an expansion of alien trees in the floodplain. And then a third one was an extreme scenario of water alien expansion in the catchment. Then the simulated results showed that groundwater depth, it showed a reduction in the groundwater depth under both water scenarios, the water expansion scenarios. And prediction results also indicated that it would be a 5% decrease in the average annual catchment yield with the floodplain water expansion, as well as a 38% decrease in the average annual catchment yield under the extreme water expansion. Another interesting result that we got from this modeling showed that waters have a great impact in the floodplain and riparian areas where water is readily available. So the actual ET, the change in actual ET per unit area increase in IAP was high under the floodplain scenario compared to the water scenario. And similarly, that was the same result with the runoff. There was a net decrease in runoff in the floodplain than in the water, in the extreme expansion scenario. So using these results, we can guide restoration efforts, particularly in this case, clearing of waters should be focused in the riparian areas where the invasives are using a lot of water. So using a similar approach in Cathedral Peak and Jonkershoek catchments, we aim to improve the understanding and simulation of hydrological processes and mechanisms of water flow for improved modeling and resource management in these 2 catchments. And just a bit of background to the Cathedral Peak and Jonkershoek catchments. These sites were established and instrumented since the 1930s and the 1940s. So we have long-term stream flow and precipitation data to use for modeling and also to explore the impacts of land cover change on hydrological processes. The Jonkershoek was initially established to monitor effects of afforestation on stream water yields, whilst the Cathedral Peak was established as an experimental site to monitor grazing, fire regimes, and afforestation as well. And since the establishment of these sites, many land cover changes have taken place. And we also aim to use remote sensing to refine some time series of land cover changes to use in the modeling as well. So I intend to use landscape analysis, hydrometric data, isotope and hydrochemistry data to inform the structure of the model and also for prediction of the impacts of land use and land cover changes on hydrological processes. So this is just a map to show Jonkershoek catchment and some of the sub-catchments. And this is a map from the Cathedral Peak with some of the established sub-catchments. So this is the data that we'll also be using for this proposed project. The majority of the data is already available, but we will be establishing some monitoring sites, particularly in the Jonkershoek, and we also would like to continue with isotopes and hydrochemistry to improve model calibration using tracer findings more quantitatively. And we hope to improve the understanding of catchment scale responses to the different land uses and land cover changes, and also to improve modeling of these critical water source areas. Thank you.
Okay. Hi, Faith. Thanks for the presentation, and excited about the work that you're planning to do. Does anybody have any questions about either Faith's previous work in the Chrome catchment, field work, or the modeling, or the plans for upcoming work? I can't see any hands. I'll ask
in the chat.
I see one from Tommy just saying that he had
Okay.
to leave early, unfortunately. Let's see. But I have one for you, Faith. Faith, what do you think is what's different between the Chrome catchment, for example, and then the Jonkershoek or Cathedral Peak in terms of what the catchment responses might be? Do you see anything that's going to be notably different that would make, that we can compare between them, or similar?
I think with the Jonkershoek and the Chrome, since they're all in the TMG, I think the aquifer properties might not be too much different, so there will still be groundwater contributions to stream flow, but the land cover changes that have taken place might be a main factor. That's where maybe we'll get a big change or a big difference.
For people who don't know, the Chrome catchment is it's a satellite site of one of the SAEON sites. So hopefully some monitoring will continue there in the future as well. Does anybody have other questions? If you're interested in any of the other more detailed results, we can pull them up. And don't see any hands. I'll ask one more. Faith, just in terms of the Jonkershoek, what kinds of additional measurements would you like to add to the site? Do you have an idea yet, even if you don't?
With the Jonkershoek, I was thinking of installing some piezometers. I still have to find out the areas where Retang had flow data with the pressure transducer stuff, and also I need to put piezometers and continue with the isotope sampling.
Great. Hopefully in a little while, once got some more data for the site, we can present.
Yes, because I think with the Cathedral Peak, it will be a bit difficult due to logistics. So we just have to work with the data that's available and also the isotope research that's ongoing there. But with Jonkershoek, I can probably do some more monitoring.
Great. Thanks, Faith, and thanks everyone for coming. If anybody has any questions in the last minute or so, I'm not seeing hands. Great. Well, thanks everyone for coming, and at the next seminar will be on the 5th of August by Laura Atkinson from Egagassini on a benthic troll experiment. measuring change in the southern Benguela slope after cessation of trawling. And if you have further insights or questions for Faith, you can find her on her email address. It's ft.jumbi@saeon.nrf.ac.za. Thanks again, and we'll look forward to seeing everybody next time.
Thanks, everyone.